Hello, welcome back to the next part of our lecture, where we talk about content-based recommendations. So far, when we built our vectors for movies, vectors for books, for other things, we used metadata, for example, information like tags, to create these vectors. The difference now is we want to be able to build vectors based not on metadata, like how it was tagged or how often it was watched or liked or shared. We want to use the actual content that we represent. So for a movie, we could use the description or summary of a movie. If you're looking at a blog post or a post on a social media website, we can look at the actual content that was written and not just the tags it was associated with. So this technique we can apply to any kind of content. Primarily here we're going to look at written content. It is possible to create content-based recommendations also for things like images and videos, but some of this we'll discuss a bit later when we talk about deep learning. For now, we just talk about textual content, like a blog post, a movie description, or a news article. So you'll see that the technique we use is the same as before. We're going to build vectors. We create a vector space model, and we're going to use cosine similarity to find out what to recommend. The difference now is that the vector represents the content of the document. So not the tags or other information, it's the actual content in there. So this is a very fundamental algorithm that goes back to document search engine, document indexing engine, and is actually the foundation of the very first web search engines. So let's look at how we can index documents. And in this example, we're going to index all the works by Shakespeare. So we have all the different plays, Anthony and Cleopatra, Julius Caesar, The Tempest, Hamlet, Othello, Macbeth. And then here we look at all the words that appear across all these different books. So this is our vocabulary. So we have the list of all words appearing across all the different books. So a couple of thousands of different words. And then the simplest index that we can build is a binary incidence matrix. So if this word appears in this book, we say, yeah, this is contained, this is a 1. And if this word, like Anthony, is not appearing in this book, like The Tempest, then it's a 0. So now we have for each book a vector of the dimensionality of how many words there are. So this is our vocabulary. Let's say we have 10,000 words, then each document, each book is a vector in 10,000 dimensions, where the individual values in the vector are either 0 or 1. So this way we can already quickly find, let's say we're interested in a search scenario, like a web search where you type in some keywords and you want to find matching documents. You can say, okay, I'm looking for Caesar. And then you can say, okay, you can quickly return all these documents because they contain the word Caesar. And if you're interested in Caesar and Cleopatra, you can look at these and intersect them with these documents, and then you return only the ones where both appear. So now, if we had a classroom setting, I could say, okay, isn't this good enough? Or is there something you can't do when we just have this binary 0-1 representation? Well, you can think about it for a few seconds. If you want, you can pause the video before I give the solution. And the solution basically is that there is no way to rank the documents. We cannot say that one is a better match than the other. So again, let's go back to Caesar. We are looking for documents. Before we could just say that these documents here contain Caesar, and therefore they all have an equal rank. Why is there a 1 here, but a 0 here? That is strange. Well, just ignore that. The point is that here some documents like Julius Caesar are obviously a lot more relevant than a document like Hamlet, where it's just mentioned twice. So if you want to be able to rank documents, yeah, like we do in a search, you give the top n, then a simple count isn't enough. So one thing we can do, and this is what we did here, we are building a count vector. So what we did is we counted in each document how often the word appears. So in this document, Caesar appears 232 times, and here in Hamlet, Caesar appeared only twice. So this is a count vector. Again, the dimensionality is the same as many words as there are across all the documents. Note that when we are building a model like this, we don't care in which order the words appear in the document. So if you're making this kind of count for 2 documents, John is quicker than Mary, and Mary is quicker than John, and you just count the words, then the count is going to be exactly the same. So first, this is why it's called a bag of words model, because it's like you put all the words in a bag, you shake it, and then both documents have the exact same result in terms of the word count. You can also see that in terms of semantics, they are quite different. They mean something completely opposite. And well, one of the interesting things is that even though this is a very simple model that throws away a lot of information, it's still quite useful for many tasks, like internet search and also for recommendation. So let's look at how we can now build vectors out of documents. So the first number that you've seen in the table just before, this is called the term frequency, TF. So this simply is the word count. How often does that term appear in that document? So how often does Caesar appear in Julius Caesar? 227 times. How often does it appear in Hamlet? 2 times. So this is called the term frequency of a term for a document. So that's the first measure. And with term frequency alone, you could already build a table like this, and you could build these count vectors. But as you'll see, coming from here to here is just the first improvement. We can do another improvement in giving a better representation on how important that term is for that document. Essentially, you can ask yourself, how do you get a high number, meaning saying, or how important that term is for that document. And basically, there are 2 different ways. That word can appear very often in the document, but this can also depend on how long the document is. Yeah, if a word appears 10 times in 2 different documents, but one document is 10 times longer than the other, then they are still different in terms of relevance, because in a shorter document, it appeared more often. So essentially what we want is to have a not just a simple count, but a representation on how important that word is for a specific document. So here we are going to do another refinement, and we're going to look at how frequent a term is, not just for a document, but in the whole collection. And the motivation behind this is that terms that are very rare, they are more informative than terms that appear very frequent. And we want to give a higher weight to these rare terms when we do a retrieval or a recommendation. So for example, you have a word that's very rare, like arachnocentric. then you want to give this word, if you find it, a higher weight than a word that appears very often. Like consider a word that is extremely frequent, like the or a. These words appear everywhere and they would get a very high count, but they are not as informative as a word like this, which might appear only a very few times in your whole collection. So that's the goal where we want to get at. We want to give, well, for words that appear frequent, we want to give them a higher weight, but we also want to take into account how rare a term is. So words that appear very frequently are not going to be as important for ranking than words that are not so frequent. So the frequent terms, you still want a positive weight, but they're going to have a lower weight than the words that are a lot more rare. So how can we calculate this? Well, we want to find out how rare a term really is. And for this, we're going to calculate the so-called document frequency. And document frequency is exactly the opposite. Here we don't count how often a word appears in the document. Here we count how many documents do have this word appearing. So that's the document frequency. If this word only appears in one document, then the document frequency is 1. If we have another word, like, again, let's say a word that appears everywhere, like the, we have 1,000 documents and it appears in all 1,000, then the document frequency would be 1,000 because it appears in every document. So now we're almost there. Now what we have to do is just to take the inverse of the document frequency, because the less often it appears, the more informative it is. So this is why we take the inverse. And this is calculated with number of documents divided by the document frequency. And you'll see we are taking the logarithm of this weight for basically scaling purposes. To see how this works on an example, so we have a couple of terms here, and we have 1 million documents. And now we want to compute the inverse document frequency using this formula I just showed you. So n is 1 million, and the document frequency is given here. So we have the word Calpurnia, which appears only in one document. On the other end of the scale, we have the word the, which appears in every single of these 1 million documents. So now if you do the calculation for the, you have 1 million by 1 million is 1, logarithm of 1 is 0. So this word that appears everywhere has a weight of 0. Now it doesn't help you to discriminate at all between the 1 million documents. On the other hand, Calpurnia appears in only one document. So 1 million divided by 1 is 1 million, logarithm base 10, 1 million, 1, 2, 3, 4, 5, 6 is 6. And the other words are in between. So here you can see how the log scaling works and what you get for the inverse document frequency rate. So a rare term, meaning it appears only in a few documents, gets a high weight, and a word that's very frequent gets a low weight. So now to get the final weight that we put into these vectors, we just combine these two together. And this is called the tf-idf weight. And this is a very important measure in document retrieval, information retrieval, and other vector space models. And this is simply the product of the tf weight and the idf weight. And because we log scaled the df, we're also log scaling the tf weight. So the formula is we use 1 plus log of the tf weight times the log of the df weight, the IDF. So you see this mentioned in lots of different places, and often it's named slightly different. You see it as tf-idf, tf.idf, tf times EDF. This is all the same thing. It's all the same calculation. It's just written differently, so don't get confused. So to summarize, what we do is we build vectors, one vector representing a document. Document, again, can be anything with content, a blog post, a news article, a movie description. And each weight in that vector is calculated using this tf-idf weight. So here, there's a simplified example on the worksheet to compute a tf-idf vector. And when you're done with that, you can come back for the last part of the lecture. See you then.